Hi, welcome back to Lesson 3 in Unit 9 of AP Calculus. We're going to be looking at solving separable differential equations that involve the natural log. So a very important set of differential equations and initial value problems involve the natural log function. Let's take a look at y prime equals y. Let's generate a slope field for this differential equation. So if y prime is the slope of the tangent line, this is simply saying that the slope of the tangent line is equal to the y coordinate. So when the y coordinate is 1, the slope is 1. When the y coordinate is 0, the slope is 0. When the y coordinate is negative 1, it'll be negative 1. And then negative 2 gets steeper. Then negative 3 gets steeper still. And then even steeper than that. Whereas over here, we get a little bit steeper. Steeper. Because at 3, the slope is 3. And up 4, even steeper. So we can see we had this equilibrium solution at y equals 0. But then everywhere else, if we're a little bit above it, we're going to shoot upwards. If we're a little below, we're going to shoot downwards. Given that y equals 0, y of 0 equals negative 1, we're going to draw a particular solution. So y of 0 means the x value is 0 and the y value is negative 1. So just kind of follow that slope field and then see where it sends you. It sends me down something like this. And then back like this. We're going to use the separation of variables technique to solve this initial value problem. So the separation of variables technique means that we're going to want to rewrite this where all of our dy's and y's are on the same side and dx's and any x's are on the same side. So it would be beneficial to rewrite this as dy dx, since that's another word for y prime. And what I'll do is multiply the dx to the right and divide by the y. So I get dy over y is equal to dx. I'll then integrate both sides. And the integral of dy over y is the natural log of the absolute value of y. And the integral of dx is simply x plus a constant c. Now I'm going to exponentiate both sides to solve for y. And I'm going to do that before I plug in the y of 0 value, because I want you to see how this works. Because this is a technique that is really important, especially in the next lesson. So I want to show you how we can change this c and where it's at and get rid of the absolute values. So when I do that, e to the natural log of y becomes the absolute value of y. And then on the right, I get e to the x plus c. But if you think about it, if you recall that something like x cubed times x to the 4th, that's equal to x to the 7th because you just add 3 and 4. I could think about this e to the x plus c and realize it was e to the x times e to the c, because in that situation, I would just add the x and c. But now that I've got that, e to the c, that's just some constant. So I can write this as c e to the x. Usually with the capital C in that case. I'm not so sure why the c is always capital. And I moved it in front. And this is what will happen, is that people will automatically make e to the x plus c, c e to the x. Now, the question is, do I need my absolute value bars anymore at this point? Well, the answer is no, I don't, because absolute value of y is saying that y could equal either positive c e to the x or negative c e to the x, and negative c and c are both c's. So by doing that technique, it allows us to get rid of the absolute value bars, which are really nice. We were told that y of 0 is equal to negative 1, so I will simply plug in negative 1 for y and 0 for x. E to the 0 is 1, so negative 1 is c. So we have y equals negative 1 e to the x. All right, let's take a look at another one. Let's solve this initial value problem. All right, I'll divide both sides by y, and I'll multiply both sides by dx. And then we'll integrate. This gives me the natural log of the absolute value of y is equal to 9x cubed over 3, which is 3x cubed plus c. I'll then put e to the both sides, and I get the absolute value of y equals e to the 3x cubed plus c. But for the same reason that we showed earlier, I can realize that this is the same as times e to the c, and then get rid of the absolute value bars and just call e to the c some c times e to the 3x cubed. I'll plug in my initial condition that when x equals 0, y is negative 2. And so I get negative 2 equals c. So y must equal negative 2 e to the 3x cubed. All right, now there is no example 3.3 for some reason, but we'll just skip the 3.4. All right, let's rewrite y prime as dy dx. That helps us separate our variables. And I'm going to multiply both sides by dx and divide both sides by y plus 3. So when I divide by y plus 3, the y plus 3 comes over here, and the dx goes over here. We'll integrate both sides, which gives me the natural log of the absolute value of y plus 3 equals, you might prefer to rewrite this as negative x to the negative second power times dx. So the x squared on bottom becomes x to the negative 2 dx. So this becomes a negative x to the negative 1 plus a constant. When I exponentiate both sides, I'm just going to do my little trick all at once here. Get rid of the absolute value bars, and that c is going to come down in front. And I'll even write it like that. X to the negative 1 becomes 1 over x. I think it looks cool. All right, let's plug in... let's go ahead and move the 3 over first. And I'll plug in a 2 for x and a 1 for y. So 1 is equal to c e to the negative 1 over 2 minus 3. So this becomes 4. I guess I could have left the 3 over there. And c e to the negative 1/2. So if I divide both sides by e to the negative 1/2, I'm really multiplying both sides by e to the positive 1/2. So this becomes 4e to the positive 1/2 equals c. And I'm kind of running out of room, but let me bring it over here and rewrite it. So I want you to see this. So we have y equals 4e to the 1/2 e to the negative 1 over x minus 3. And the way this is typically written is the 4 stays there, and then we go back to using our properties of exponent and call that plus 1/2 right there in the exponent. So the exponent is negative 1 over x plus 1/2. Then I have a minus 3 on the outside. Okay, I do have some practice problems for you to try. Got, I think, just 3 of them. So pause the video if you can, please, and or try each one and then have me go over it with you and then pause it again. So try practice 3.1. All right, hopefully you divided both sides by y and multiplied both sides by dx. We can now integrate both sides, and I get the natural log of the absolute value of y is equal to the natural log of the absolute value of x plus c. I can then exponentiate both sides, and I get y is the absolute value of y is equal to e to the natural log of the absolute value of x plus c. But we know that we can split that apart and call it this. And e to the c, that's just some c. E to the natural log will actually cancel out, leaving you with just the absolute value of x. So I have the absolute, I don't need the absolute value anymore on the y. The question is, do I still need it on the x? And the answer is no, you don't. It's just c times x. That's all we need to handle that. So y equals cx is the solution. Oh, sorry, we need to find what c is. So let's do y of -1 is equal to 2. So 2 is equal to c times a -1. So a -2 is equal to c. So y is equal to -2x. And I want to point out that that is not the it's not the absolute value of x. It's actually -2x. So if I want to have the y coordinate divided by the x coordinate be the slope, for example, let's take a look at it. When x is -3, then y is equal to 6. Then 6 divided by -3 is equal to -2. And then down here, let's say when x is 3, y is a -6. Again, I need to have the y over the x, which is equal to -2. So it turns out getting rid of those absolute values is quite important. All right. Are quite acceptable. If we did use the absolute value bars, it would have just come up like this, but that would also end up giving us the same kind of situation. But it's typically written just like that. So kind of an interesting problem. The absolute value bars are kind of weird there. You can remove them so that typically they are, but if you kept them on, it would still be true as well. All right, let's take a look at this one. I want you to draw a slope field, sketch a couple solutions, and then I assume we're going to solve the differential equation. Let's try it. All right, dy over dx equals x over y. So when x is 0, dy dx is 0. So it would be just like that. Now, not when x and y are 0, you get 0 over 0. We're not going to look at that. When y is 0, though, you get a vertical tangent line. And then at 1, 1, we get 1, a slope of 1. 2 over 2. So all of these are positive ones, and all of these are negative ones. All right, and then we have when, let's say x equals 1, y equals 2, we get a slope of 1/2. This would be a slope of 1/3, and you see it's just flattening out, right? When it's a -1 over 2, it's a -1/2. And so I think you can see what's going on here. Let's take a look at over here. -2 on the x, 1 on the y. That's going to be a -2 slope. So they're just kind of pulling towards each other and then flattening out towards these diagonal lines. So close to here, they're flat, and then they get more and more shaped like that diagonal line there. And I'm not being super careful right now because I think we've already got the idea. All right, let's take a look. Well, that last one was pretty bad. Hold on. I was getting a little too cavalier there. There we go. All right, let's graph the equation through -3, -1. Well, that would be kind of like this. Now, if it's just a function, that's all it's going to get. It's not going to come back up here and keep going. If it's in a relation, it would. Let's take a look at -1 and 2. Well, that one would be going like this, and then it flattens out, and will actually curve back up. So this is the fabled hyperbola branch here. All right, so we should expect some sort of hyperbola. Let's solve the solution. And we're going to solve it for f of -1 equals 2. So we're going to get the equation that was this blue portion here. All right, so we have dy over dx is equal to x over y. So I get y dy equals x dx, and I'll integrate both sides. So y squared over 2 equals x squared over 2 plus c. If I multiply both sides by 2, I get y squared equals x squared plus 2c. Well, that's just a c. Plug in a negative 1 for x and a 2 for y. So 4 is equal to 1 plus c. So 3 equals c. So y squared is equal to x squared plus 3. That's our answer there. Let's take a look at when the differential equation goes through negative 3, 1. Well, everything will be the exact same, right? Up to here, y squared equals x squared plus c. But now I'm going to plug in a negative 1 for y. Oh, you know what? I left this as a relation. I didn't actually get the square root. And if I take the square root of both sides at this time, I have to use, so I'm going back to this one. I have to use plus or minus. But because I need a positive 2, I'm going to take the positive square root. That would give me y as a function of x. All right, now we're ready for this one. So 1 is equal to 9 plus c, so c equals negative 8. So y squared equals x squared minus 8. And I need to take the square root of both sides to get y as a function of x. But because f of x is a negative value at negative 3, I'll take the negative square root of x squared minus 8. All right, one more problem here. I got a slope field to consider. And I want you to find the solution with the initial condition that g of 0 equals 0. That would probably look something like this, right? So see if you can't figure that out. So that would be dy over dx is equal e to the negative y. So dy over e to the y, e to the negative y equals dx. Well, I can just rewrite that as e to the y dy equals dx. You know, if I have e to the negative y, I can multiply both sides by e to the positive y. Or if you divide both sides by e to the negative y, then use your properties of negative exponents to move it up. Either way. The integral of e to the y is e to the y plus c. And the integral of dx is x plus c. So in this case, we're not getting natural log in our integral, but we're going to use natural log to get the y down. So it's going to be y is equal to the natural log of x plus c. Now we were told that y of 0 is, or g of 0 equals 0. So 0 for y and 0 for x. So the natural log of what is equal to 0? Well, that's the natural log of 1. But we could solve this doing algebraic stuff. Put e to the both sides. E to the 0 is 1. So 1 is equal to 0 plus c. So either way you slice it, c is equal to 1. So our equation is y is equal to the natural log of x plus 1. And that is it for this lesson.